Okay, well, I guess we can get started. This is the last of the geodynamics lectures, and I, in some ways, wanted to start by going back to the beginning. The very first Monday, Michael introduced us to dimensionless numbers. And dimensionless numbers get used a lot in geodynamics. In fact, during the informal discussion that happened prior to the lecture series, I was having a discussion with Jackie Lee, and she was complaining about the fact that geodynamics community uses dimensionless numbers, and that it was probably as confounding as when geochemists plot ratios of isotopes, ratios of elements against ratios of elements. And so I disagreed with that point of view. I think the geochemists stand alone on this, in terms of confounding. But what I wanted to do was to just show you why dimensionless numbers are kind of useful, because we're going to lean on some of this stuff as we go through this lecture. And so I just wanted to show you a little bit about these things. Dimensionless numbers really are just one facet of a larger field, you might say, of dimensional analysis or scale analysis. And there's a gem of a little book by Barenblatt on scale analysis or dimensional analysis, I can't quite recall. And it's a beautiful little book, and if you're at all interested, I encourage you to have a look at that book. So I had said in the very beginning that geological activity was all about convection. I still stand by those statements. I still believe that that's true. And I just wanted to show how you can use dimensional arguments and sometimes just a little bit of physical intuition to completely characterize systems and be able to sort of predict how they're going to behave beyond the range that we can actually reach in numerical calculations. That's the idea. So the problem that we have, and the problem that we've been talking about, the problem that Kanane ended with, was the notion of convection in a planet. And so if you bring some layer up to some hot temperature relative to the surface, the depth is some particular value L that I'll describe. Eventually this fluid will begin to convect and will develop a temperature profile which will be different from that. It will have steep temperature profiles in the thermal boundary layers. This is still delta T, as before. It's still L. And the point, I guess, is that the convective system is very effective at moving heat through the planet. So you get fluid motions in the interior. These are very capable of moving heat through the interior. That's great. But the problem, or the bottleneck in this process, is actually getting the heat out the top. Because unless you have sort of massive amounts of volcanism that you can physically erupt the hot material to the surface, you've got to get the material out of the volume by conduction. And so you have to develop these very thin boundary layers where thermal conduction dominates. You have to make those thin enough to be able to get the heat out. And in some ways, thinking about the heat transport in a convecting fluid is really all about thinking what are the processes that are going on in setting the thickness of that layer? Okay, and this approach or this theory is sometimes described as boundary layer theory. And so we know that if we were in this state, that the temperature that we would conduct out along this temperature profile would be essentially this. And so convection, in essence, gives us a way of cooling the planet much more vigorously than we would be able to if convection wasn't possible. Okay, and Alan introduced us to the notion of dimensional equations, non-dimensional equations, the idea that instead of using meters and seconds and kilograms, you use other units, other rulers, if you want, to measure quantities that are more suited to the problem. Okay, and the typical length scales, or sort of the typical rulers that we would use the length as a typical length scale. Very often we use a time scale, which is a diffusive time scale, like L squared divided by the thermal diffusivity will give you a time scale. That's very common in mantle convection. Sometimes in core convection problems, we'll replace this with a magnetic diffusivity. Various sorts of choices, and that's why Hero's code in terms of Calypso was really quite useful, because you could change the non-dimensionalization to the problem that was most of interest to you. Okay, so the Boussinesq equations that Alan introduced us to were this. There was the momentum equation written in non-dimensional form, and let me just write coordinate axes here. See, so there was the pressure effects, the buoyancy effects, and the viscous effects. and I'll use U, I guess. I think Alan used U too. So in this particular context, there's a bunch of forces. This is where the accelerations would be, but for a sticky mantle, the accelerations are pretty small, and so we don't worry about that. The temperature equation, Michael introduced this to the material derivative, which is this if we don't have any heat sources. And finally, the conservation of mass equation was this. And so the reason why non-dimensional equations are really, really powerful is that by making a few simple assumptions about how the system works, you can completely characterize it based on what are the dimensionless numbers that appear in your equations and other things. So for example, in this process, you can imagine what's happening here at the top, right? You're getting cold fluid that's forming at the top. It gets cold, the layer thickens as it conductively cools. It gets unstable and it drips off, okay? And the same thing is probably happening at the bottom, this bottom thermal boundary layer. Fluid is getting hot, it's heated up, it gets buoyant enough to become unstable, and it rises up, okay? And so if you could make the assumption that the processes that are going on right here, in terms of forming these drips and having them sink down, are largely independent of what's going on at the bottom boundary. So you could make the assumption, a reasonable assumption I would claim, is that what's going on at the top is really determined by processes that are in the vicinity of the boundaries. And the same thing at the bottom. And so one of the ways that you could sort of characterize that is to say, let's suppose that this Q, this heat flux that's coming out, is entirely determined by processes here, and it's completely independent of L. Does that sound plausible? We can vote. Actually, the mineral physicist told us yesterday that good answers can be obtained by voting, right? So we can just maybe, rather than sort of vote, who thinks that this is a good idea? We can just put up your hand. Okay, so the rest of you think that this is a nonsense, right? Okay. Okay. You're going to be disappointed. If I make the assumption, the only assumption I make is I imagine that the heat flow is determined by just things that are going on in the vicinity of the boundary layer structure, that this heat flux is independent, this physical heat flux is independent of L, I'm telling you that I've completely specified the convective system and can predict anything, almost. And it's kind of neat. Okay, let's see how this works. So I'm saying that Q is independent of L, by virtue of it being really a boundary layer process. And so I can now start to think about things that I might be interested in, like the Nusselt number, which was the ratio of the heat flux divided by this conductive heat flux, the hypothetical heat flux that we would have gotten if there was no convection. And let me just remind you what the Rayleigh number was again. It was alpha G delta T L cubed divided by the thermal diffusivity and viscosity. So I'm using kinematic viscosity, so there's no density there. And the other thing that's amazing about dimensional analysis is this is a non-dimensional quantity. It's a non-dimensional heat flux. It would come from this system of non-dimensional equations. And because the only parameter that appears in these equations is the Rayleigh number, that I know that that has to be a function of the Rayleigh number. There's no alternative to it. Okay? And so if I think about what the conductive heat flux is, and I put that in, I have Q, I have L, I have K, and I have delta T. Yes? Oh, question.
There's one other parameter that appears in the equations as you've written them, which is kappa.
Oh, my apologies. It should be gone. And it should be gone because I defined my time scale that way. That was my error. So the only parameter that appears when I do it correctly, when I write them correctly on the blackboard, is the Rayleigh number. Okay? So that's a good point. Thanks, Lars. So here's the issue. What does this function have to be such that this non-dimensional heat flux is a linear function of L? Well, it's got to be the cubed root of the Rayleigh number. And I'm done. What you guys did in your tutorial with aspect was more or less prove this result. So those of you who put your hand up and said, yes, I believe that those two boundaries are doing independent things, you're correct in the sense that that assumption then leads to a prediction which actually is consistent with numerical results. It's not usually perfect, but it's pretty good. And it's often the basis for doing things like parameterized convection and other sorts of things, what we would normally want to do is say, I want to know Q, so I take the Nusselt number, which is the third root of Rayleigh number, multiply it by this hypothetical conducted heat flux, and I can get the heat flux out of a convecting system, say the mantle, going back in time using different values for delta T. So it's a very, very powerful thing. John Arnaud came and talked a little bit about rotation. And the main thing that we did when we added rotation is that we added the accelerations back in. We added, this is a funny, hopefully you'll forgive me for dropping density. This often happens. So we added the accelerations back in. I could also add the centrifugal effects, but you could nominally argue that they could get absorbed, for example, into the gravity vector. And if I used exactly the same non-dimensional scheme that I had used to set up the mantle convection problem, I would introduce some additional dimensionless numbers here. I would have the inverse of a Prandtl number, and Prandtl number is viscosity divided by the kinematic viscosity. And I would introduce right here the inverse of another number, which is the so-called Ekman number, which is 2 omega L squared. And we're going to see all of these numbers coming back up again. Now the problem is it's not so easy to figure out how the heat flux is going to vary. Now, in principle, it could be a function of the Prandtl number, and in fact, it could be a function of the Ekman number, and now it's not so clear. And in fact, there really isn't a good theory that describes as concisely and as neatly as the mantle convection problem when we have the addition of these extra properties. Okay? So to me, the dimensional analysis is really not about confounding the audience or other fields, but it actually has some real power, and it makes predictive estimates, which is really useful. Okay. Yeah, questions? So we can. Well, I think that's it.
Just in question, when we consider a rotating system, how far off the Rayleigh to the third system do we actually get for the current Earth?
Okay. So yeah, that's a fair point. So we can go along. I tell you that there's published estimates that are way off. So there's some estimates that suggest the Rayleigh number to the third power, for example. Ekman number typically enters in. I would say the most likely is probably Rayleigh number to the 1.5. And there's an Ekman number dependence, roughly an Ekman squared dependence, which are the most popular. But the point is, once you sort of have the system set up, you can get these scalings. And the reason why we care about them is because we can never run the numerical simulations at the actual conditions. But if we can get the physics right, the basic physical processes right in the models, then we have reasonable confidence to actually get us to Earth-like values. I'm going to argue at the end that, in principle, I don't think we're in the right physical regime with our dynamo models to be able to extrapolate the Earth. And I think there's going to be real surprises as we go forward and actually look at these problems.
Yeah, one more quick question there. What about heat production in the interior?
Sure. So that's another one. And that would, in that standard problem, that would introduce an additional dimensionless number. You could imagine that way, right? And the way I would do it was to do the same thing and make the assumption that the boundary layer is independent of the depth of the fluid, walk through the same argument, and you would get the appropriate scaling, which would be what? Rayleigh number to the 1/4, I think, is the usual estimate. So, okay. But that would be in the case of totally internally heated. That's the one I'm imagining. If you start mixing them, and then, of course, it's more complicated. Okay, so let's turn our attention now to lean on these results and turn our attention to planetary dynamos. And so here's a picture of the Earth. This is an image that was created by Eric King. This is actually liquid gallium that he used from the lab when he was working with John Arnaud. And in the center is actually solidified gallium. So that's the inner core solidifying as the core grows. We've talked a little bit about mantle convection. It's a solid material. It convects. It's really not a fluid in the normal sense, although, as Uli has shown, it behaves laws that look fluid-like, and so we can characterize it in terms of these ideas. The liquid outer core, on the other hand, really is liquid. It has a viscosity which is probably 10 to the minus 3 Pascal seconds, something like that. When you think about the kinematic viscosity of this material and account for density, its effective viscosity is probably a little less than water. So it's very, very fluid. And because that viscosity is so low, it turns out that temperature anomalies in the convective system could be on the order of just a few millikelvins, as compared with hundreds of degrees in the mantle.
So I ask my usual question,
Yes.
how do you know the viscosity of the...
Well, how do we know? Well, so one of the things that you do is you ask, well, what's the viscosity of liquid iron at ambient pressures? And we know what that is, and it's pretty low. And then you could ask, well, could pressure do something to that? And the answer is it's hard to do viscosity experiments at high pressure. Raymond has tried. But mostly we rely on the density functional calculations to tell us this. And what those calculations tell us or suggest is that pressure is not a big player in terms of the effect of viscosity. So we think that's okay. And you know, the thing is, in order for this, yeah. So there was a group, I have to say, that said, you know, these numerical dynamo models, they look so good. Maybe the problem is that the viscosity is way higher than we thought it was, and that actually we have the models right. In which case the viscosity is about 10 orders of magnitude higher than what we're currently doing. I think it's safe to say that the viscosity of a liquid is not on the order of the viscosity of, say, effective viscosity of ice. So I think those things are probably okay, but there is probably some uncertainty. Okay, so the scientific questions, I guess, for this problem are really how do we organize fluid motions in the core that are able to interact with the magnetic field and allow us to regenerate that magnetic field. And this is a numerical simulation from one of Hero's calculations. What you're actually looking there is at the vertical component of vorticity. So if you think of fluids that are rotating around or spiraling like this, you take out your right hand, you point your fingers in the direction of the spiral, and your thumb points in the direction of the vorticity. So these are vertical vorticities, so they're fluids motions that are spiraling around like this. And those motions are very, very helpful or constructive in terms of regenerating magnetic fields. So that's, in some ways, the science question of the dynamo problem per se. But there are other issues, I think, that are much broader and maybe of much more interest to this particular group. And that is that planetary dynamos are really very useful diagnostics of internal dynamics broadly across the entire planet. Here's an example of Earth, and we know that Earth has a magnetic field. Venus, which is our sister planet in many respects, similar size, probably similar composition, similar in many ways, doesn't have a magnetic field, and it's probably related to the nature of the internal dynamics of Venus. The fact that Venus doesn't have plate tectonics is probably enough to explain the differences. And so, similar story with Mars, no magnetic field at present, evidence of magnetic field at early days, which is a suggestion that the geological activity of Mars was much more active, much more vigorous at early days. So following a little bit on Kanani's talk, if we wanted to do extrasolar geology and we wanted to know something about the geological activity of extrasolar planets, one way that you might be able to do it from space, at least in principle, is to be able to detect magnetic fields on these guys. So how you do that, that's a challenge. Astronomers will eventually figure it out if it's worth it. The other point, I guess, is what about the early fields? So if I've made the argument that magnetic fields are really sensitive diagnostics of the internal dynamics, what do we know about the early field? And this is the great part about this subject, is that we have evidence of fields going back at least to 3.4 billion years. And I would make the claim that this is evidence of plate tectonics on Earth at this particular time, or something very much like plate tectonics that is able to transport heat out of the planet as effectively or nearly as effectively as plate tectonics does it today. Okay. So let's start talking about some of the physical processes. So here's a picture of our present-day state of the core. We have the mantle, ultimately setting the amount of heat that's going to come out of the core. It's the player. It's the 800-pound gorilla in the room. It sets the pace, and then everything else follows as a consequence of what the mantle decides. And so we can get things like cooling. We can cool it fast enough. We can get the entire core to sort of gradually cool. It will thermally contract a little bit. This will cause the surrounding core fluid to crystallize, and the inner core will grow. We can get cold fluid, which is produced at the top boundary layer, which will drip down, much like in that mantle example that I was showing you on the blackboard. The phase change will produce latent heat, which is a source of buoyancy. And we've also heard a number of discussions during this two-week lecture series of the impurities that are dissolved or evidently in the liquid core that give rise to the density deficit relative to pure iron. And we also know that the density deficit in the inner core is less. And so that some of these impurities are being excluded, and this gives rise to an additional source of buoyancy which can essentially drive flows. So all of these sources of buoyancy are going to stir a core which has very low viscosity, which is very rapidly rotating, and somehow these flows are going to be able to generate and regenerate the Earth's magnetic field. And one of the really key things, I would say, in terms of trying to decide the relative importance of all of these different elements of buoyancy is really thinking about the heat flux that's coming out into the base of the mantle. So here's a plot of the present-day temperature. This is an interesting plot for a couple of reasons. One is that I made this figure in 2002. It was for the Francis Birch 50th anniversary. And I was looking at this plot before I came, and there's not too much on this that I would actually change, to be honest with you. I might bring some of these high temperatures down a little bit, but not very much. So in some sense, we haven't made that much progress, I guess. So mineral physicists, back to work. Paul, get the iron on the laser, I guess, or the shock experiment. But we know something about melting temperatures. We know thickness of oceanic crusts. We know something about temperatures near the surface, mantle temperatures near the surface, and we can extrapolate those down to the base of the mantle and get estimates sort of in this range. And as Paul also mentioned, we know something about the melting temperature of iron, although hotly debated, and we can extrapolate that up along an adiabat, say, knowing the densities and the Grunheisen parameters, to get sort of estimates of the core side of the boundary sort of in this range. And clearly there's a difference between these two, and these two differences are essentially the thermal boundary layer between these two that is allowing for heat from the core to enter into the mantle. So that range of temperature anomalies, perhaps as low as 1,000, perhaps almost as high as 2,000 degrees. So still a lot of uncertainty. If we zoom in on that boundary, so here's the picture. There's our extrapolation of the adiabat down to the core mantle boundary. Here's the extrapolation of the adiabat up to the core mantle boundary from the core side. There's the temperature difference. We can use simple convective models, much like the boundary layer model that I was describing earlier, to make estimates of how thick we think that layer is. That's another prediction that comes out of that model. If we know something about the thermal conductivity, the thickness of this layer, the temperature difference across that thing, we can make estimates of what the amount of heat flow that would be coming out of the core integrated over the surface of the core, and it's something on the order of 5 to 15 terawatts or so. You could ask, and the question's asked here, is there a thermal boundary layer on the core side? And the answer is we don't know. Actually, there might be, and there might not be. But if there is a thermal boundary layer on the core side, it's probably not more than a couple of degrees. And so the idea of attributing most of this temperature, or really all of that temperature anomaly, to the mantle side is a pretty good assumption. Okay, so one of the things that's really interesting about terrestrial dynamos generating magnetic fields. Yep, sorry. Yep.
I just wanted to clarify. The only difference between whether you're attributing it on the core side versus the mantle side is a different K, right? I mean, it's still the same delta T, wouldn't it be?
No.
Or I guess a different delta as
well.
well.
What I'm saying to you is that it's possible to have a temperature anomaly, boundary layer temperature difference on the core side. But I'm telling you, or I'm asserting to you, I guess maybe is a better way to say it, I'm suggesting to you that the amplitude of that temperature anomaly is probably not more than a degree. I would make the claim that once you subtract off the adiabat, right, because there's a large change in temperature. So how much is the super adiabatic gradient in the core? How big do we think that is? That could be less than a degree. Okay? So it's tiny, right? We're talking about millikelvin temperature anomalies. We're talking about super adiabatic temperature gradients, which might be integrated over the core a couple of degrees. So I'm asserting that if there's a boundary layer here, it's probably not bigger than a degree or two, period. And so that most of that temperature anomaly has to be on the mantle side.
Does the boundary layer theory break down if delta gets too big?
It does. Yes, it does. I mean, in some ways, boundary layer theory is best when the Rayleigh number is high. And so the question that you might ask, though, is maybe this isn't a simple thermal boundary layer.
Right.
And that's also a valid point. So there may be more physics going on than just what the simple model suggests. And that's a good point. And so a fairly generous range of estimates for this delta went into this. A fairly generous range of estimates for the K went into this. And you can see there's a factor of 2 to 3 variations in the estimate of the heat flow that's coming out. And I think that that's probably a pretty reasonable range.
So for the thermal boundary layer on the core side, could that be influenced by having a light buoyantly stable?
Oh yeah, it could be
homogeneity at
influenced.
the
Yes,
top?
yes. Okay, so there, I think I could imagine pumping that estimate up a little bit higher, that temperature difference a little bit higher, in a sense because that temperature difference is not really now playing a role in the dynamics. It's entirely contained to a stratified layer, and it's not a player anymore. But you're right. I could play around with that a little bit, but not very much. It's mostly here. Okay? Good.
I don't think everyone would agree that the range of thermal conductivities you've allowed for is generous.
Yes.
There are a lot of nutty ideas running around about both the lattice and the radiative thermal conductivities of the lower mantle that are much more than a factor of 50%.
Yes, yes. The problem, radiation is one of these things. It seems to be on a 10-year cycle where sort of every 10 years someone says, wait a minute, oh my God, the mantle is transparent and the light is just streaming out of it. And then it goes away. And so I've developed the perception that I don't pay much attention to these things. But the truth of the matter is you don't need very many impurities in these ideal systems that you can have a huge effect on the radiative transfer. And so, yeah, right. Enough said, I think. Yeah, Michael.
Mark asked whether it's the difference in thermal conductivity that gives rise to the differences in the two delta T's for the boundary layers. And it's the difference in viscosity.
It's really the difference in viscosity that plays a huge role. That's right. I mean, in some ways, the fact that you've got these millikelvin temperature anomalies, the fact that you've got these sort of small superadiabatic temperature gradients, are all about what temperature anomalies do I need to drive the flows that we infer from magnetic field variations. And those velocities are large by virtue of the fact that the viscosities are very low. Very low. In many problems that I do, I'll assume that the viscosity is 0 for all practical purposes. Right? It's just not there. And I think in terms of a convective system, I think that's a pretty good assumption, actually. Okay. Here's the interesting thing. Here's what I think is the most interesting thing and what makes terrestrial dynamos such a good and sensitive diagnostic of internal dynamics. Okay. Should we stop for this question, or should we introduce this first?
I just want to point out the difficulty of the phrase conduction along an adiabat.
Yes.
Because the definition of an adiabat is the thermal gradient you get in the absence of heat conduction.
Well, okay, I'll put it slightly differently then. What I would say is that if I have a system which is in thermal equilibrium, what I mean by that is that it's well stirred, it's well mixed, and the way I think about it is that when I move parcels around, when they come into some new neighborhood, do they exchange heat with their neighbors? And if they don't, then that's a thermal equilibrium state. And there's no question that you will get a profile which is pretty close to adiabatic if the fluid is well stirred. And there's also no doubt that that's a temperature gradient. And there's no doubt that there will be conduction down that temperature gradient. Yes. And so I think both are possible. Now, clearly, if this value, what I'm going to show you, gets too big compared to the heat that's being transported, then there's a soft edge, the soft shoulder that we could roll over onto. But I think that this is pretty reasonable. And part of the reason why I think this is reasonable is that the core is, presently at least, is being really well stirred by compositional buoyancy. And so I think the issue of having a lot of thermal conduction is not a problem. But that's a good question. That's a good point. Okay, so now I'm ready. So that's actually a good segue. That's a good setup for this. Because we take this adiabatic gradient, this what I'm thinking of as a thermally well-mixed fluid that has a gradient, and this depends on temperature, it depends on pressure and such. And I multiply it by the thermal conductivity of liquid iron, which is pretty good. I mean, the thing that makes iron a good electrical conductor, makes it good for generating magnetic fields, also makes it good for conducting heat. And so if I take that adiabatic gradient and multiply it by the values of thermal conductivity that we've had, say, prior to the last couple of years, that we get values sort of in the range of 5 to 8 terawatts, which is a lot. That's a significant fraction of the amount that the heat that the mantle is taking out. Okay? So the point, I guess, is that the mantle is not driving the system very hard, that the core can't completely supply everything that the mantle asks for by conduction alone. And so if it was only thermal conduction, then potentially this is a system that could fail. And that's what makes it useful. Because if it fails at a certain geological activity, then that's a boundary that we'd like to understand. Okay, so a couple of years ago, the first paper I think came out in 2012. This is an update to do iron alloys. What's being shown here is a plot of the electrical conductivity as a function of pressure through the core. So the top of the core is here, and the core mantle inner core boundary is sort of roughly about here, I guess, 330, I think, something like that. And the point is that these numbers are about a factor of 2 higher than what I would have used, say, 5 years ago. And so if you go back to that plot and you put in these new thermal conductivities, you get values that are now sort of in the 10 to 16 terawatt range. And so now these are really in the range of the values that the mantle are taking out. And now we really have to think about what's going on and how the system is going to behave. Okay. So here's one possibility. It is possible, in terms of those numbers, you can find combinations of numbers. Oops, sorry, wrong way. I wanted to go this way, I think. So it is possible that we could be up here at the 15 terawatts, and we could be down here at the 10 terawatt limit. And so this value could be bigger than that value, and that's not implausible. If that did happen, here's the story that you'd expect. So we imagine that the light elements and other things are going to keep the fluid well mixed, so that we are going to have a nearly adiabatic state. We're going to have conduction along an adiabat, and we're going to be taking more heat out. The mantle is going to be taking more heat than you can supply by conduction down that profile. And so as a consequence, this fluid is going to cool. I'm going to get a thermal boundary layer in this particular case. This is going to go unstable. It's going to sink into the interior. I'm going to get these sorts of things. And that advective heat transport will balance these two things out. Okay? So that's perfect. We get a thermal boundary layer. This is the picture that's actually taking place in the core. That's certainly possible. And that's what I would have thought 5 years ago. But it's also possible, and increasingly possible, or increasingly likely, that the heat flux that the mantle is taking out of the core is actually less than you can supply conducted through a well-mixed core. And so what happens now? Well, you have a well-mixed region. Okay, it's maybe mostly mixed by light elements. You get conduction, bringing heat toward the boundary faster than the mantle can take it away. So two possibilities. One is that you just simply start to warm this region up. So this will become a warm, dense, warm fluid, sort of like hot air rising and then just sitting at the top of the ceiling. It's also possible, though, that compositional buoyancy could potentially mix this fluid and bring warm material against its wishes back down into the interior. But I think, and for reasons that I'll show a little bit later, I think the amount of inertia in these flows is sufficiently low, and I'll show you exactly what I mean by that I think it's very unlikely that this warm layer is going to get mixed back down into the interior. So it's likely that this thermal layer a thermally stratified layer would develop at the top of the core in this particular context. Okay? So I've got a layer, it's stratified, it's hot, it's sitting up at the top. I would still get convection in the region underneath here, but this layer would essentially be stagnant. It wouldn't be participating in the convection. And some interesting things start to happen. We get compositional instabilities because as the inner core continues to grow, it's continuing to release light elements. But that light element is only being mixed into the region down here. So this is building up a region that's compositionally light eventually with time, where this is thermally light. And when you have the battle between these two sources of buoyancy, you can get things known as double diffusive convection, salt fingering type instabilities, and this could actually bring some of the light element and mix it back up into this region. But you would definitely then still have a thermally stratified layer at the top. So
how big a temperature effect are we talking about here over time? Is this warm layer degrees, tens of degrees, or hundreds of degrees?
Yeah, this is on the order of a few degrees.
Okay.
This is on the order of a few degrees.
So not enough to influence the ability of the mantle to export that heat.
No.
Because if you heat the core mantle boundary layer by a couple hundred degrees, the whole behavior changes.
Yeah, it would completely change that. That's right. And this also makes it almost completely invisible to seismology. But it is visible to some things, and I won't have the time to talk about it, but this buoyancy, this stratified layer, will give rise to waves. And I think we see those waves. And I think the Earth is marginally in this state. And so it's kind of in a state where its future is assured, but its position in that world is kind of on the edge. And that's why I think the dynamos are such useful and interesting diagnostics of dynamics.
So Bruce, did you say how thick that layer might be?
Well, it sort of depends on how marginal this is. And so I would say if the difference between these two heat fluxes was sort of on the order of 10%, let's say this was this heat flux was 90% of the adiabatic value, then my guess is this layer would be probably about 100 kilometers. And as this difference gets bigger, this layer gets thicker, and it's pretty clear that it can't be arbitrarily thick. But I think we have evidence for the fact that this layer exists, and I think that it's just marginally in this state. So if we think about an early Earth, and I'm going to show you when the inner core, or perhaps when the inner core appeared, with no inner core, with no sources of compositional buoyancy, with no way to mix the fluid, if you have this possibility that heat flux is higher than the adiabatic value, then you will produce this source of buoyancy. You will mix the fluid. You'll generate a magnetic field, I suspect. On the other hand, if this value drops below this, as I'm suggesting our current state might be, then very likely convection would cease and the dynamo will fail. And it's very likely that that's what's happening in Venus today. Venus, without a plate tectonic regime, with a stagnant lid regime, which is much less effective at transporting out heat, is probably not drawing enough heat out to get the core to convect, and it just simply shut off. Yep.
Is it possible that both two cases coexist in different regions of the Earth?
Yes, it is. I know that Dave Gubbins has made the argument that all you need is this to be exceeded in one place. I've never understood those arguments, to be honest. I don't think that that's right. But I'm sure locally that you could probably have regions where the heat flux is greater than the adiabat. But I would argue this. My intuition would tell me that if most of the core mantle boundary was subadiabatic, the heat flux was subadiabatic, you had a thermally stratified layer, and one place where you pumped in a little bit of buoyancy, dense material, it would just simply spread itself around through the stratified layer. It wouldn't drive very much convection. But it's possible, of course. Yeah. Okay. So here's yep, sorry.
So talking about convection seems a little bit scary. Number one. Number two, what would the time scale of this transition between having convection and not having convection?
Geologically, a heartbeat. I'm going to give you some numbers.
So like the movie The Core?
Yeah, it's going to be exactly like the movie The Core, actually. So this is a little digression. Do we count this as a discussion? Actually, when I was at UBC, they filmed the movie The Core, actually. And they came to me and said, we'd like to have some props, some images that we can use to sort of demonstrate this movie. And I thought, well, Gary Glatzmeyer has great images, right? And so I said, you should give him a call and see what he says. And at the next AGU, he came up to me and said, these crazy people called me about this crazy movie and wanted to use these images. And I said, absolutely not. And I never told him, I never actually told very few people that actually I put them onto him. But it's out of the bag now. So it is public now. Sorry, Gary. It's been a long time. I'm sure he forgives me. There are some qualifications here, though, and this was one of the things that came up a little bit earlier, was there are other energy sources, and the problem is that we don't know enough about them to quantify them. But it is possible that you could have an additional source of chemical buoyancy. And the idea is that if you dissolve lots of light elements into the core when it's very hot, and then as you cool, you exsolve those light elements back out of the core, then essentially by taking the light elements and, say, plastering them under the bottom of the mantle, you leave behind a compositionally dense liquid that can drive convection. And so that's possible. The current experiments suggest that both silicon and oxygen are undersaturated in the core relative to equilibrium with the sort of a nominal mantle composition at these pressures and temperatures. But there are other elements, in particular Dave Stevenson has really promoted the idea that magnesium as a dissolved element, very small amount perhaps in the core, could play an important role. So there are potentially other energy sources that we haven't considered that could be important, that could get around some of these difficulties. Okay. Okay, let me give you a little bit of a primer on convective power, because what we'd like to know is how to take these buoyancy fluxes, or this amount of convective energy, and make estimates about how much power we've got available to drive convection. Question? Yeah.
Going back to Dave and magnesium.
Yeah.
In the sort of second sense, when you have a conductive layer on top of the core itself, wouldn't something like exsolving magnesium actually make that unstable, because you'd be exsolving magnesium at the very top of that thermal layer, which would make it compositionally dense and therefore fall again, and that would break all that
sure.
up.
So if compositional buoyancy is playing a role, then compositional buoyancy from the top could mix the layer potentially, right? Sure. Yeah. No problem. Right? Yeah, no, absolutely right. So compositional buoyancy could completely eliminate thermal stratification. The reason why I don't think that's happening is because I think we see evidence for waves that require buoyancy stratification, but that's maybe a circular argument. Okay, so let me give you a little bit of a primer, because what we'd like to know is how much power have we got available to drive convection? How much work can we do? And so here's a sort of an idealized picture of a convecting system. We've got heat flow in the bottom. We've got heat flow in the top. We develop this sort of temperature structure, which I described before. We get convection. It's able to do work. In the mantle, this work is deforming the material, driving plate motions. All of those things are the work that convection does. In the core, it's doing things like generating magnetic field and producing ohmic currents. The analog, I guess, that I would give for this is that if you've ever walked through Isla Vista, say at 7 o'clock in the morning, and the party's still going on, right? And you were to go to one of the amplifiers that was playing the music, and you put your hand on it, it's going to be really hot, right? And so that's the source of dissipation. It's the current that's going through this liquid metal, which is not perfect, which will produce heat. And that's the way that we measure the amount of work that's being done. It's kind of the exhaust of the dynamo process. But whatever the dynamo exhausts is the energy that it's consumed to produce the field. So it's a useful diagnostic for thinking about how much mechanical work I do. And so if I look at just the energy balance, the energy equation, and the energy equation for sort of a fluid like this that's not evolving with time, the temperature is not evolving with time, requires that I put as much heat in the bottom as I take out the top. That's a simple statement of energy conservation. Okay? And I noticed actually when Alan was showing his equations that he sometimes included this term as an additional term in his temperature equation. And so I'm going to ask you, if you have any thoughts, of whether or not I should be thinking about the dissipation as contributing to the heat flux coming out of the system. Shouldn't I just add it? It is a heat source, right? So I've got heat going in, I'm driving convection, I'm doing lots of work, I'm dissipating energy. Surely that heat will then contribute and come out of the system. What do you think? Seems reasonable? Yeah? So the answer is it's not reasonable. It's bad. Okay? Because this energy, this dissipation is just the consequence of converting energy from one form to another, right? If I ask what's the temperature of this thing, and I come back later and the temperature is roughly the same, then the thermal energy of this thing is exactly the same as it was before, right? So whatever heat I put in, I had to take that heat out to keep that system in the same state in an integrated time average sense. And so the point is that this energy, or this dissipation, is really just a part of the process of transferring this heat energy from one form to another. And so anytime when I see a thermal equation, a temperature equation that has the dissipation explicitly in it, I look for the other pieces of the temperature equation to make sure that the processes are in play that will take that heat out, so that no contribution from this actually takes place. And it's kind of neat. I like it, so I'm going to tell you about it. If you don't understand it, you can just pretend like I was just mumbling for a couple of minutes and just ignore it. But here's the idea. The adiabatic temperature gradient, the rate at which temperature changes with pressure, depends on temperature. Okay? So I've got a hot plume at the bottom boundary, and I got a cold plume at the top. This guy's hotter, right? So its adiabatic gradient will be steeper. And so when it goes to the top, it will cool a lot. Well, more than a parcel which starts cool with lower temperature will warm as it goes down. There's an imbalance in the heat that's produced by the compression, and that imbalance is cooling, and that cooling is exactly what absorbs that heat. And so dissipation should not contribute to the global energy balance. Okay? What do you think? Not neat? No? Okay. But the point, I guess, here's the key point, though, that's important, is that if I look at the energy balance alone, I can't say anything about the dissipation that's going on in the core. If I want to know something about how much work is being done, I have to look at the entropy balance. And you often see this in papers, and these are probably parts of the papers that you may ignore, but it's actually pretty powerful, okay? So if I'm putting in heat at a certain rate, then the amount of entropy that I'm putting in is basically that heat divided by the temperature that I'm putting in at, right? So this is the ds equals, dq by t, and now this is just expressed in terms of a rate. So I'm putting entropy in at the bottom at this rate. I'm taking the same amount of heat out at the top, but because the temperature is different, I'm taking out a different amount of entropy. I'm putting in less entropy than I'm taking out. And if I want to balance entropy, if I want sort of a steady state, I must be producing entropy somewhere inside here that will balance this. And one of the ways that you can produce that entropy is with the dissipation. Okay, so this is the angle, or this is the thread that you can use to get access to what that value is. And so here's the value. The value out is much larger by virtue of the lower t. Here's the value going in. The imbalance then is just the dissipation, the entropy production due to dissipation in the interior. I can think of that as like the global dissipation divided by some average temperature, rearrange and get this expression, which looks a lot like a Carnot efficiency. It's saying if I know how much heat I'm pumping through the system, I know the structure of the temperature field, I can say how much mechanical work I can do. During the informal part of the discussions, there was a suggestion that one way that you might be able to drive the dynamo is by pumping heat in one place at the core mantle boundary and taking it out at another place. And the reason why that fails catastrophically is the fact that the temperature along here is probably the same within a few millikelvin. And you see here, it really does depend on the difference in the temperature between where you put it in and where you take it out. And so that process, at least in the Earth, would never work. It actually works in numerical models, which should give you some pause. So another way that you can produce entropy is by conduction. There's no question that the dominant source of conduction in these problems is the conduction down the adiabat. And you can sort of make an estimate of what that would be. And so now I can balance this with both ohmic dissipation, the work that convection's doing, and also the entropy production associated with conduction. Both of these will contribute. This is positive, that's positive, and so inevitably the amount of work that I'm going to do that will be available to drive the dynamo will get less and less and less as the thermal conductivity gets higher and higher and higher. And in fact, you can make a very good estimate for the influence of this contribution just simply by subtracting off the amount of adiabatic heat flux that goes to the top. So this is really a good approximation to this, that I just simply take the Carnot efficiency and I apply only the heat flow that is in excess of what can be conducted. In other words, the convective part of the heat flux. And that works really well. And so this is how we come at estimates of the power that's available for driving the dynamo. Okay. So we can generalize ideas to sort of include things like inner core growth, chemical buoyancy, latent heat, all that kind of stuff, and you get an expression that looks like this. I've got a bunch of different Carnot factors for thermal convection, for the latent heat release, for the composition. This depends, again, on the CMB value minus what you can conduct toward the boundary. Latent heat depends on the CMB heat flux minus any radiogenic heat production. And the reason for that is that it's only the cooling of the core that will contribute to growth of inner core and compositional buoyancy. And so if all the heat that I'm taking out is produced by radioactive decay, then the core won't cool. So it's only the excess. So this may be zero, but it's there if it turned out to be non-zero. And you can see plotted here these Carnot efficiencies a function of inner core radius, with the inner core radius, present-day inner core radius shown right here. The thermal efficiency is something on the order of 10%. So if I had a super adiabatic heat flow of 1 terawatts, then I'm going to be able to produce 0.1 terawatts of work toward driving the dynamo. You can see that compositional buoyancy is pretty good. It's way up here. At present day, it's probably up around 16% or something. Latent heat, a little bit less. But as you go back in time and the inner core gets smaller and smaller and smaller, these guys go away. And you're left with this. And so if this number falls below that, you're out of business. In fact, this number probably has to be a little bit bigger than this to make sure that I've got enough power to drive things. Yeah, question.
Bruce, I noticed that you have EC or epsilon C crossing epsilon T when the inner core is about half the size.
Yes.
Does that have any implication for change of inner core structure, maybe on inner core?
I don't think so. I think this will be mostly a fact. Because in some ways, this is really saying, how much will the heat flow that I take out the top, how much will this buoyancy source contribute, and how much will this buoyancy source contribute, and how much will that buoyancy source contribute to the mechanical energy? And so, you'd expect these to be smoothly varying, but you could imagine that this heat flow value will be changing all over the place with time as well. And so the actual work or mechanical work that you have could change quite a bit. So I wouldn't attach too much significance to that crossing, to be honest.
I'm having trouble seeing why the latent and compositional terms go continuously to zero as the inner core radius goes to zero.
Okay. And why is that?
Well, it seems like they should go not at like the inner core radius, but by the rate of change of the inner core radius. Or they should go like the pressure difference between the inner core surface and the core mantle boundary. And both of those are a maximum at the beginning of inner core growth.
Yes, that's true, but it's getting still multiplied by the surface area, which is vanishingly small. And so you're right. These depend on both the surface area and the rate of growth of the interface. And so roughly speaking, the inner core radius grows as, say, square root of time. So you could probably do that, so what is, I think it does vanish. That limit goes to zero, I think. But you're right. The rate of growth is infinitely large at early times. It goes as 1 over square root of time. But then the radius of the inner core, the surface area of the inner core also gets smaller as you go back. And those two go to zero.
Yeah, I guess those aren't really efficiencies anymore if you're grouping those terms in there. They're sort of efficiencies times magnitude of the energy source. Somehow. Well,
okay, but I mean, you're right. I mean, so embedded into this term here and embedded into that term there will be things like the current radius of the inner core. And these heat flows then tell me something about the inner core growth rate. So here's the geometry, and then this difference is the inner core growth rate. And so, yeah, you're right. It's the product of these two that ultimately determine the energy. And so knowing this part is really just the geometry part, and then knowing this piece is the growth rate part, if you want to think of it that way. So and now I'm even more certain, because now I'm just looking at the geometry part, whereas here's the growth rate. This is the thing that you're imagining, that the dt gets really big. Yeah. But the bottom line is that when the inner core is gone, this is our only friend, right? And so if that goes away, it's a lonely planet. Okay. So here's just an example of what the consequences are. What I'm looking at is the heat flow as a function of the value that you assume for thermal conductivity. And so I've written the typical values. So this is from a Goldschmidt meeting from a few years ago. I knew that this result was coming, so I anticipated and went out to 100, right? But these were sort of the typical ranges. So for example, if we thought the thermal conductivity was something on the order of, say, 40 in SI units, then the amount of heat flow that would be conducted along an adiabat would be something on the order of 5 terawatts. If you wanted to get a dynamo power of, say, 0.3 terawatts, plausible, with thermal convection alone, imagine going back before the inner core existed, I would need to have roughly 3 extra terawatts of heat dropped by a factor of 10 to get this value. So I'd need to be up here around 8 terawatts of heat to get that amount of dynamo power. But if I now go up to 100 in SI units, the amount that's being conducted down the adiabat is almost 14, and the amount that I need to get that amount of dynamo power out is a little over 16. Okay, so here's the consequences for the thermal evolution. Here's heat flux of 16.5 terawatts. It's that point. This green curve is just imagining that heat flow at the core mantle boundary stays constant for all time. So I go back in time. Actually, I noticed this. When you see people do evolution calculations and you ask, what's zero? Is zero the initial time, or is it the present time going past? You see this a lot in paleoclimate literature, right? And I think like ocean people do things different than atmospheric people. So this is time before present. So here we are today. If we had 16 terawatts of heat coming out of the core and was constant all the way back through time, then the inner core would have formed about a little bit more than 500 million years ago. And then we would have sort of evolved up to these sorts of temperatures. These are temperatures at the core mantle boundary at the earliest stage. If we try to do some sort of crude boundary layer analysis where the heat flux is proportional to the 4/3, which just comes out of that Nusselt number, Rayleigh number relationship, then we evolve along this curve, assuming that viscosity doesn't change. But in fact, it's likely that in a hotter planet, viscosity would be very different too, and there would be additional complications. And so all of these results, and even if it was just 8 terawatts, we're still only looking at an inner core of 1 billion years. And so during all this time, going back to about 3.4 billion years, we know that we've had a magnetic field, and we know that it's been sustained by some manner of convection in the core. Okay. So let me use the last little bit then to talk how the magnetic field gets generated. How does this work? So we've talked a little bit about the buoyancy sources. We've talked a little bit about how we quantify the energy that's available to the dynamo. How does the core actually do it? And it goes back to a set of equations due to Maxwell, the same Maxwell that gave us Maxwell relations. I'm guessing it's the same Maxwell who's Maxwell's demons, probably, right? So he had a lot of thoughts, a lot of ideas. In fact, most of the things that go into this equation actually predate Maxwell, to be honest. But the approximation that we often use is the so-called MHD approximation, which is the idea that the fluid velocities involved, these v's, are slow compared to the speed of light. So in a sense, we're kind of filtering the propagation of light, which is a pretty safe assumption. And so the evolution of the magnetic field B evolves in response to these two terms. One is the motion of a conducting fluid through the magnetic field will produce electric currents, which then regenerate the magnetic field. And this piece is the diffusion. Okay, this is the diffusive piece. So if you subtracted this piece away, you went down to here with no flow, you're basically in a purely diffusive state. And if there's no sources of magnetic field, there will be a characteristic time scale for the magnetic field to diffuse away. And it's sort of on the order of 25,000 years. Maybe a little bit higher with these more recent electroconductivities. But to come back to your question about how long, pretty short amount of time and the field's gone. So, and there's no evidence for the field ever disappearing from the surface of the Earth. We don't have continuous measurements, of course, but the number of places where we could have the field shutting off and then turning back on is not extensive. And so it's likely that the field has always been generated, and so it's always managed to do this task. We have estimates for the fluid velocity that are largely based on the way the field changes at the surface, and we can make estimates of what we think the magnitude of this term is relative to this term. And we think it's sort of roughly on this order. If you remember Michael's definition of the Reynolds number, that was velocity, a length scale divided by the kinematic viscosity. This is called the magnetic Reynolds number because we've substituted in the magnetic diffusivity for the momentum diffusivity. For the core, it's probably on the order of about 1,000. And we know that we need, for suitable fields, we need values that are probably on the order of about 10 to make this process work. Okay. So let me just point out briefly the nature of convection in the core. John Arno talked about this, and we had great discussions about what the flows actually look like. I'm going to try to illustrate these for you a little bit. Here's the momentum equation. So I've got the local inertia right here. I've got the Coriolis effect. I've got pressure, buoyancy, and viscosity. And so we can do the same thing that Michael did in terms of looking at the relative importances of the different terms. So for example, we can ask how big is this term relative to the Coriolis effect, which we're used to thinking about in terms of atmospheric motions. And the answer is it's really small. It's 10 to the minus 16. Tiny. So tiny that if we could get rid of this term and still run our numerical models, it would be a good idea. But we just can't do that. How about inertia? How about the importance of these terms relative to the Coriolis term? This is the Ekman number, and this number typically goes by the name of a Rossby number. Okay? And it's also really small, 10 to the minus 7. So inertia, these terms are negligible by comparison with the Coriolis force. And so basically, I think at least anyways, of this term being the turbulence term. That's the thing that plays the critical role in turbulence, and it's utterly negligible. A real pet peeve of mine, and I guess this is on tape, I won't name names, but what's the ratio? What's the ratio of this term over that term in words? This one divided by that one. It is. Well, it is big, but what is it? Physically, what is it? What is it? It's big, of course. It's gigantic. It's 10 to the 9th, right? But what is it? Inertia over viscosity. Do you remember what that was? That was the Reynolds number, right? And if you do this ratio, you'll get the Reynolds number back out. And people will often say the Reynolds number in the core is gigantic, and therefore it must be very turbulent. And it's simply not true. It would be a little bit like going to a bank manager, and the bank manager says, okay, you want a mortgage from us. What are your assets? And you say, well, I'm pretty wealthy compared to the 4-year-old down the street. My guess is he's not going to loan you a lot of money, right? And the reason is being big relative to something that's negligible doesn't make you big, right? You're still small, and so, right? And so it just doesn't work. And so that's a sore point with me a little bit. So that's why I'm bringing it up. And you won't make the same mistake. Okay, but when we do have magnetic Reynolds numbers that are big-ish, sort of hundreds to thousands, you can think of the influence of flow on the magnetic field as the flow actually takes the magnetic field with it. The term that we often use to describe this is frozen flux. So it's like the magnetic field line is kind of frozen to the fluid and goes wherever the field or the flow goes. And so what I wanted to do, just kind of briefly, obviously, is talk a little bit about how we generate the dipole part of the field. This is just one part of the story, but it's the part that we see at the surface the best. Okay? So this is an image that I've taken from Wikipedia, and it just points out that if you have a current going through a wire like this, and that wire, that loop has some surface area, you multiply that current by that area, and you get a dipole moment, which sort of measures the strength of the magnetic field. And we do exactly the same thing in the core, except we're not confining the currents to go through wires. It can go through anywhere. But we can have a current density, so this is amps per square meter instead of just amps. But amps per square meter circulating around sort of lines of latitude essentially will give rise to a magnetic moment. And so this is what the core is doing. It's producing currents that are sort of swirling around like this, and they're producing the dipole field that we see at the surface. And so in the absence of external sources, in other words, in the absence of any generation that's outside of the core, which we think is the actual case, you can actually take this expression and rewrite it as this. This is not too hard to show. You can look this up in Jackson's book, for example. But the point is that if you want to know what the magnetic moment is, you just simply have to integrate the orientation of the magnetic field through the volume of the core. This is just the magnetic permeability. We just assume the value for a vacuum, essentially. So if I want a magnetic field that has a dipole field like this, so the moment is pointing in this direction, all I have to do is get my field inside the core kind of preferentially pointing in this direction. So how do we do that? That's all that we need to do. That's all the models need to do. Okay. So the idea behind this goes back to a really classic paper of Gene Parker in the mid-50s, who pointed out that if you started with this particular configuration of magnetic field, a loop of field which is existing in the interior of the core, and it's easy to generate these fields by a variety of processes. So easy that we don't even need to assume that it's there. It's a very solid assumption. And then we have some kind of helical convection. Okay, its fluid is rising. It has some vorticity to it, in other words, some circulation around like this, that it will lift this field line and twist it. Okay? And this can produce current in the plane perpendicular to this, and maybe somehow that works. But if we go back to this expression right here, it's not obvious how this is going to work, because sure, okay, I'm thinking about, say, the z component of the magnetic moment, so that's the axial part of the dipole. Then I need to line up these BZs. And I see I've got a little bit of a BZ here. All right, that's good, but then this piece completely cancels it. So it looks like there's going to be a lot of cancellation in terms of this. And it's not quite clear at this stage yet how Parker's idea is going to work. But what happens in the models, essentially, what the numerical models suggest or show, is that if you have these two filaments of field, one going up and one going down, and then you can have the flow separate them. You separate these two components, you take one and you push it out, you expel it from the core so that you're only left with the other one. Then you can actually contribute to this magnetic moment. And that's actually what the models do. It's sometimes called the alpha effect for reasons that are the same as alpha decay is called alpha decay, I think. If someone else had written the paper, it would have been something else, I'm sure. Okay. So here's just a schematic from one of Peter Olson's early papers that really illustrated this idea. So there's your azimuthal magnetic field. You've got these convection columns, which we know arise when you have rapidly rotating convection. Again, just to sort of orient you for the vorticity, because I'm going to show you. So in this particular case, so this column here is positive vertical vorticity, so that's pointing up. This guy is the other way, so it's negative vorticity. Okay, and you've got flow going up one column and going back down the other. So what you tend to find is convection columns which have different sense of vertical vorticity neighboring each other. Okay, so what happens here? So okay, this is coming up. This flow is coming up, so it's going to carry the field line with it this direction. This one's going down, so it's going to carry this field line down a bit. But then look at these flows. This flow is going inward, so it's actually going to suck this part of the magnetic field and pull it in toward the core. And the neighboring pair on this side, the column on this side, is pushing the thing out. And so this part of the field is going to get pushed out. And it's doing the separation of those two elements. And so here's a numerical simulation. It's one of Hero's calculations. Okay, what is being shown is the vertical vorticity from one of these numerical models. So you can see positive vorticity in the hot colors and negative vorticity in the blue colors. You'll see that they're not just columns, right? They're more kind of sheets. Okay, so you've got sort of long circulation around these sheets, right? As well as you've got upwelling or downwelling in these different colors. And so what's happening is the vorticity is basically lifting the field, taking the one element and pushing it all the way to the core mantle boundary, pushing it out of the core, taking the other piece and accumulating it on the inside. And that's essentially how these guys work. And so if we were to look at the magnetic field that gets produced by those flows, what you end up getting is something that looks like this. You've got positive field sort of congregating in the center, the sort of hot colors, and you can see the vestiges of the field with the opposite direction. So this is the vertical field component, the one that we want to line up to get the magnetic moment. You can see the vestiges of that as it's actually being pushed out of the core. And these are very, very efficient at generating dipole fields. They're very, very good at it. They're way more efficient, for sure, than the Earth's core actually is. But as a proof of concept, it's great. It shows that fluid motions in a rapidly rotating system can, in fact, reproduce and generate magnetic fields. And it's, in some ways, it's been almost say a disservice to the community that the models have worked as well as they have. Because a lot of people think that the problem is solved. And I think we've got big problems. So let me just use the last couple of minutes to talk about some of the challenges for these numerical models and why I think there's big problems ahead. This is a quote from a paper, or probably a book by Richardson. He was the first guy to try to do numerical weather prediction with paper and pencil, essentially. And I would imagine, right, that the forecast would come in long after the weather come past, right? But I guess I want to illustrate the point with this. He's really thinking about classic turbulence, and I've told you that turbulence in the classical sense doesn't exist in the core. But it's useful to set a physical point of view that I want to have in your minds. That big worlds have little worlds that feed on their velocity, little worlds have lesser worlds, and so on to viscosity. And so the idea is that in classical turbulence, you have this sort of cascade of energy down to smaller and smaller and smaller scales, and then eventually those scales see the viscosity, and that's what terminates or sets the limit of the small scales in the flows. And even Leonardo da Vinci, in this sort of 1590 picture of water flowing into this thing, had the basic ideas, right? So you see these large circulations, and then they're feeding littler circulations, and then so on and so forth down. And so the point, I guess, is that viscosity you can think of as being a momentum diffusion, really. And so that's ultimately going to what sets the length scales in these flows. So even though turbulence is probably not so important, there's no question that viscosity is going to be the thing that ultimately limits the length scales of the flows. And similarly, magnetic diffusivity, which is just 1 over the permeability and the conductivity, okay, sets the limit of the magnetic fields. So the magnetic fields will sort of be produced at small scales, but eventually once you get to a small enough scale, magnetic diffusion will just erase those. So that will set the scale of the magnetic fields. And so when we look at the physical properties of metals, they're pretty different. The viscosity, typical values of viscosity, sort of on the order of 10 to the minus 6 meters per second, meters squared per second. Thermal diffusivity is a little bit higher, maybe an order of magnitude higher. Magnetic diffusivity is sort of on the order of 1. So coming back to those parameters that I had mentioned earlier, the Prandtl number is about 0.1 in the mantle. Anyone remember what the Prandtl number in the mantle is? What is it actually? Maybe 10 to the 23, something like that. So 10 to the 23 is close enough to infinity that you just simply say 1 over that must be obviously 0, and out goes inertia. But here, actually, inertia is not negligible. Coriolis effect is a dominant effect. But the magnetic Prandtl number, the ratio of the velocity scales that are possible to the magnetic scales that you would expect to see, are very, very different. This is 10 to the minus 6 for typical liquid metals. And the other interesting thing is that when the first models came online, the best models tended to have magnetic Prandtl numbers that were bigger than 1. And generally speaking, the bigger you made the magnetic Prandtl numbers, the more Earth-like the solutions got. Okay? So the solution to getting Earth-like values is to push the parameters in the opposite direction, right? It's kind of telling you that there's maybe something not right, right? It's more complicated than that, but that should be a hint that things are a little bit funny. Okay. So this is a plot. This is one of the really one of the best numerical solutions that we've done so far. It's by Chris Jones and his co-workers. This has gotten to an Ekman number of 10 to the minus 3 times 10 to the minus 6. So again, that's the ratio of viscosity to rotation. So the viscosity is pretty low, so we're allowed to have pretty small length scales. So you can see some small length scales developing in these flows. The other point, I guess, this is an equatorial plot. Okay, so it's a slice through the equator, and you're looking at the radial velocities. So you can think of these flows almost like plumes. You can almost think of these red things as rising up like plumes and these cold things sinking down like cold downwellings. But what you have to remember is they're connected to a structure which extends up and down really between the two boundaries. Does that make sense? I guess what I would love to know is whether that actually helps the physical picture of what John was talking about, right? Where's the heat going, right? And most of the heat actually gets transferred from the equator of the inner core to the equator of the core mantle boundary in these calculations. But again, what you have to remember is those structures that extend in the vertical direction that are also moving along with this buoyancy. And that's the structure of the flow that's really important for generating the magnetic fields. Here, the magnetic Prandtl number is 0.1, okay? That's a really good value, because generally when you get down to this value, the models fail. And you can see that the structure of the magnetic field is much larger scale than this. And so where the numerical models have to go is they have to go to much smaller Ekman numbers, which means much smaller velocity scales, relative then to the much larger magnetic scales that actually emerge. And we actually don't know whether or not, well, I guess we sort of know that this has to work because we have an example of it working. But conceptually, it's not obvious that this is going to work, because as these velocity scales become smaller and smaller and smaller, their magnetic Reynolds number, that was the ratio of induction to diffusion, was V times the length scale divided by the diffusivity. And as you make that length scale smaller and smaller and smaller, you make the magnetic induction effects weaker and weaker and weaker. And it's actually not clear, if we were to push the values to these parameters, that everything's going to work out okay. And so I wouldn't be at all surprised if in the next, say, 5 years or so, as computers get better and we can run these solutions on bigger and bigger computers, and we're certainly headed in that direction, as we start to push these parameters more and more toward Earth-like values, I wouldn't be surprised if there's a fundamental change in the way in which these models work, and that we're going to have to then reappraise really virtually everything that we've done up to this point. I think with that, I will conclude and take any more questions, actually, if you guys have them. Okay, all Dynamo converts. Yeah, Brent.
So there's that heuristic model where the magnetic flux, the magnetic diffusivities are not zero, and so you talked about in those models you need for the flux change through time to not be the field lines to move with the flow.
Yes, right.
Okay.
So you can imagine as you start to, so that's a good point. So as you imagine you start to restore viscosity or diffusivity,
right,
the field lines are now slipping through the flow, right? And as you go to very, very low magnetic Reynolds numbers, the field is hardly being distorted by the flows because the length scales are so small. And that's the problem.
And so will that model kind of change as you change this length?
Well, that's the question, right? That's the question. And so it's pretty, I would say that it's unavoidable that the structure of the flow has to fundamentally change as the Ekman number gets small. And the hope is, or the thought is, that somehow the magnetic field and the influence of the magnetic field on the flow will be unhappy with the small-scale structures and force the convective flows to be large-scale. So now suddenly the magnetic field is playing an important role in the structure of the convection, and then it saves us. So the magnetic field essentially gets us into a state where the flows are useful in doing work to generate magnetic field.
So now the magnetic field is preventing those small-scale.
Well, with our numerical models, the problem is that viscosity is so big, so large. Actually, okay, so this is another slightly funny story. It's funny to me, I guess. I was organizing this talk. It was about trying to get parameterizations for some of these small-scale terms, and I was kind of looking for materials that would be the comparable viscosity to the viscosities that we use in our numerical models. And so I came across this pitch drop experiment, which some of you guys may have seen. It was in Australia, I guess, right? And they put some pitch, which is basically like like asphalt almost, except more viscous. and they put it in a funnel and waited for about 3 or 4 years for it to kind of flow and fill the funnel. And then it started to drip out, drip by drip. And I think each drip was happening maybe every 4 or 5 years or something like that. Is it 10 years? Okay. And so there's a picture that I found with a woman that had the dates of when it fell, right? And the argument was that their funding had been cut off because the results had become incremental, right? But the point is that very high viscosity, I think, is what prevents the magnetic fields from having an important role on the flows. Right now, the flows are completely understood by the effects of viscosity. And it seems, at least in the numerical models, that the magnetic fields are not able to exert much influence on the flows. But that's the hope, that somehow the solution is going to be transformed, and we're going to go into a different state where the field plays a much more important role. But the trajectory looks bad, I would say. And so that's why I expect kind of a transformation in the way in which this process works, I suspect. Yeah.
Bruce, in these numerical simulations, why can't you just drop the viscosity term completely?
Yeah, people have tried to do that.
Diffusivity
term. People have tried to do that. And the challenge in doing that is that then your geostrophic flows, which are the flows that are just simply flow balancing pressure, are unconstrained. And so you have no way of setting them. So you could try to use some kind of boundary layer theory to sort of couple these things and do it that way. But so far, those efforts have not been successful. Yeah. Yeah. Well, yeah. So, but still the problem is that, yeah, so the magnetic fields could play a role. But I guess people who have tried to do that, you see, you're trying to do that without knowing having much information about the structure of the magnetic field that you would get in those particular cases. And so the real problem basically is that there's a component of the flow. These would be like the winds on Jupiter, for example. Those zonal flows are the geostrophic flows, and they're unconstrained. And so the other point, I guess, is that if you reintroduced the magnetic field, then you're going to be shearing those magnetic fields. They're going to exert stresses. But if you really think inertia is really small, then those stresses over, it turns out, cylindrical columns have to be balanced. And so that's how people have tried to use the magnetic fields to do this. David Fern, I think, tried to do this with Michael Proctor 2 decades ago, and it was a disaster because they just couldn't figure out how to get the field organized onto these cylinders such that there was no accelerations. And the answer is that that's probably not right. There probably are inertial effects. But actually how you get a numerical solution to do that is a challenge. So I think we're kind of stuck with using viscosity. I think there's no way around it. And I think just simply running bigger computers, running these solutions on bigger computers, or using more sophisticated treatments for the small scale. Because I've made the argument that at some point, once you get to small enough scales, the flows aren't doing anything for the magnetic field. You can kind of ignore them. But you have to know those flows properly to get the big scale flows correct. In other words, they're kind of like a stool on which the big flows stand on. And so I think one of two things are going to happen. Either just brute force will get us there, or we'll have better subgrid scale schemes for the small scales that will allow us to represent these effects without having to specifically resolve them. And they're the only two paths.
So on that idea of the brute force, if you just, take Moore's law and figure out, how long
when will we get
have
there,
to
right?
wait before we can get small enough scales that we can deal with appropriate equinoxes,
right. So
what time frame are we looking
right.
at here?
Well, that's also hard to say because what we don't know is what the Ekman number at which this transition will take place, assuming that a transition takes place. We don't know where it is. We tend to be an optimistic bunch, and we say, it's probably just an order of magnitude away, right? But we don't know, actually, where that is. My guess is that we don't have to get to 10 to the minus 16 to get into this regime. Maybe it'll be at 10 to the minus 8. Maybe it'll be at 10 to the minus 9. But essentially, once we can get there and we get the flows into the right dynamical state, then we can use these scaling laws and actually, with some confidence, say something about what's happening on Earth at those extreme values. So the point is we don't have to get all the way there, but we don't know where the boundary is of getting into that playpen. And so, right now there's an effort to really go big time. So the CIG group has put together a proposal for hundreds of millions of CPU hours running on some of the biggest computers we've got to really kind of push these parameters maybe an order of magnitude, maybe a little bit more, and hope that gets us a little bit closer to this transition.
Bruce, I think you said we use the rates of secular change of the field to
Yes.
infer the convective velocities of the
Yes.
core.
Yeah.
This figure makes that idea very troubling because the field and the actual velocity are operating at totally different scales.
Yes, exactly right. But if I just go back for a second, I think that's a great question, Paul. Let me just go back, if I can, through the movie. Right, here's the equation that we use. And so when we use the secular variations of the field, what we're doing is we're saying that on short time scales, like on tens of years, on hundreds of years, that probably we can neglect this term. Now, we don't know for sure. But the idea is that you basically assume that that term is zero. You have observations of the magnetic field going back a couple of hundred years, and you ask the question, what velocity field will allow me to reproduce those changes with those observations? And so we make the assumption that that term is zero. If that term is not if that term is not negligible, then these flows that we've inferred are not correct. But that's where the velocities come from. My feeling about this is that the flows at the top of the core, in my opinion, are in this stratified layer. And I think the flows that we're seeing at the top of the core are some mix of kind of steady geostrophic flows plus waves. And they're big planetary scale waves. And I think the approximation is okay. The problem with that, though, is that the fluid velocities in the waves may not be representative of the flows in the interior. And that's true.
But also, we're only observing the field at the surface.
Yes. Well,
and if you
yes.
downward continue it,
Yes.
there's lots of short wavelength,
yes.
high frequency
Yes.
Secular variation that we're not seeing.
Yes.
So your velocity is only capturing the largest scales.
Absolutely right. Absolutely right. And so there's no question that when you do this, this is a nonlinear term, right? So if there are small scales here and there are small scales here, that those two small scales, neither of which we can directly sense in some ways, could contribute to big scale magnetic field changes that we would map into these guys. That's true. That's true. Right? But what do we want from this calculation? I guess what we would like, in some ways I would probably not trust the details, but the notion that we're getting velocities on the order of tens of kilometers per year is probably okay. We see patches of magnetic flux. They're big patches, and they seem to be being swept across the core, and the volume integral of the radial field going through them is more or less conserved. And so all of these are good indications that just treating this part is probably okay at those big scales, and you get an order of magnitude estimate for the velocity field. If you wanted to sort of take those flows and try to do much, much more with them, then you have to worry about these things. What is the unresolved part of the field, and what's the unresolved part of the flow doing to the part of the field that we can actually see at the surface? But you're right, we downward continue, assuming the mantle is an insulator, which is probably not too bad. But we're only getting the velocity fields probably within 5 centimeters of the boundary. That's where the free stream is, essentially. And we have no idea what's going on down below. And I think, in some ways, this wave story I like a lot. But the downside of that wave story is that we may not be seeing the actual action in terms of the convective flows. So it might be actually a step backwards in some ways. Does that make sense?
So Bruce, you've made the point that for most of the history of the magnetic field, there might not have been an inner core at all.
Yeah.
So how much do these problems change if you don't have an inner core, the structure of the flow?
So you need to have the heat flows bigger than the adiabatic value unless there's some other source of energy that we're tapping. And so that value now, if the Dario alpha's results are right, we're talking about heat flows coming from the core in excess of 15 terawatts over geological time. And for me, the big problem is, sure, okay, the core started hot, right? And we're tapping all of that primordial heat that's in the core. My concern is that if we have 15 terawatts of heat coming out now, and we go back in time and the mantle was much hotter, what's to prevent the heat flow from coming out much faster at early times and bringing you down to a stage where it's impossible to sustain those high heat flows over large geological time? So to me, the question is, yeah, okay, we can have just really hot core, that works, but actually how we keep the heat down and only take it out at 15 terawatts or slightly above as we go back in time into a hotter planet, to me is the challenge. And
I was curious also about the structure of the flow and how that might look if you didn't have didn't have that little blank circle in the middle.
My guess is that it wouldn't be so different. Actually, my guess is that it wouldn't be so different. You'd still have these helical convection columns. They might extend in a little bit further than they did before, but my guess is that people are just starting now to run numerical models without an inner core. It's been much easier to run them, the spectral codes with an inner core. It's great because all of your singularities get dumped into a region where you don't have to resolve the solution, right? So it's good. So that's the proverbial sweeping stuff under the carpet, right? But you know, people, Hero's working on this. There's a group in Etihad that's working on this. My guess is that it's probably not going to change in a fundamental way. What will be different is that you can get a separate convective regime in the cylinder that sort of is tangent to the inner core at the equator, and you can have kind of a separate convective system plus this other flow that I've showed sort of in the outside regions. And so that separate convective system would go away, and so that would be a little bit different. But my guess is as the inner core vanishes, some of these convective columns will probably extend in a little bit more, but probably not so different. But we'll see. You know, the numerical models will be done, and we'll soon see.
Continuing on a similar theme. Yeah. Can you comment on what it might look like in these exoplanets where you have a very hot surface?
Yeah. So well, this is the interesting thing about this story is that at least in principle, you can detect magnetic fields remotely, right? We know, for example, from things like synchrotron radiation in the gas giants that they have magnetic fields. There are better ways to do it than that. But the point is that you can sometimes detect the presence of magnetic fields on things. And so if you could detect the presence of a magnetic field, what it would tell you is that you're able to draw heat through the mantle of these planets much, much faster than you can conduct heat through the core in that metal, right? And so the point, I guess, is if you have very hot surfaces which are not giving you a mobile lid, that give you kind of a stagnant lid, that you have to conduct all the heat through this layer that's not participating in the convection, then you're in trouble, I think. And you know, all of these first principle calculations, as the temperature and pressure go into the interior along an adiabat, the conductivities get bigger, right? So if you imagine a planet that's bigger and an adiabat is the appropriate description for this well-mixed fluid, which is presumably convecting and producing magnetic fields, then the amount of heat that you can carry by conduction in this well-mixed state gets higher and higher and higher. And so I would say that my own guess is that unless the mantle convections really do a job in terms of getting heat out, it's going to be hard to have magnetic fields in these big guys. But we'll see. In principle, we may be able to know. Yeah.
Bruce, a lot of work hinges on the estimates of viscosity.
Yes.
And my understanding from a couple of years ago, talking to people that do that hinges on a calculation with about 100 atoms of pure iron. And I don't know what kind of uncertainty that leads to in the first principles calculation. Yeah. And there's also some controversial suggestions of higher viscosities observationally. I'm not sure we should believe them
so
or not. But
there have been some papers that suggest that the effects of pressure on liquid metals can have a huge influence on viscosity. So Doug Smiley has latched onto these in a big way. That's definitely a minority view. And I think certainly the calculations have gotten better. You know, I don't know whether the numbers have changed that much, but you know, what you're able to do now in terms of calculations is much better than before. And I haven't heard anything about values being dramatically revised. And I assume that if those values were different as computations got bigger, that one of these groups would probably be pointing out that the other group got it wrong, and we would hear about this. But maybe that's untrue. I don't know. Lars, have you heard any more about viscosity calculations? Actually, yeah, the group in Japan actually have actually done very recent calculations, and they've been looking at the details of actually how the viscosity by these density functional calculations changes through the core. And I think they're coming up with values that might be a factor of 2. Hiro, do you remember? Yeah. It's about a factor of 2, but they're low. They're really, really low, and in some ways they're a little bit lower actually than the alpha results. And they're probably going to be a little bit different for alloys, but you know, where we need to go to make viscosity really important is where viscosity is in our models today, which is like 10 orders of magnitude. And I think that's probably off the table.
So maybe I'm still thinking about inferring the velocities of the flow from the secular variation, the magnetic field. So if I'm thinking about this future state that you were kind of forecasting, in which the magnetic field,
the small scale,
and the small scale flow. Did I understand you correctly that the very small scale flow and the magnetic field essentially become decoupled? then why would looking at the magnetic field tell you anything about the velocities of this small scale?
Well, so if you were to plot the spectrum, for example, of those flows that I showed, where the scale is getting very small, what you would expect to see is kind of a white spectrum, and then it basically tails off where viscosity plays a role. So it's not like when you see those small scales that all the flow is concentrated in a small peak with a relatively narrow range of length scales. So you get it's very broad scale, right? So your eye picks up the contrasts where they're very sharp, right? But what your eye is picking up is essentially something close to the cusp of that spectrum.
Okay.
But the point is that you've got power in long scales. But I guess my concern is you dump more and more of the kinetic energy and you extend that spectrum from your perspective, as I extend that spectrum sort of white to much, much smaller scales. All these guys are going to be doing is basically destroying magnetic field, not generating magnetic field. And so it leaves the large scale flows to basically do the rest of the job. So what this gives us is the large scale velocity fields, which is sort of that one end of the spectrum. And is that representative or not? I mean, generally speaking, in other models, my guess is that the spectrum would be kind of white in terms of velocity. So I think, at least for the intermediate to large scales, that these velocities would be probably representative. And then I would expect that as you get to the cusp, the amplitudes go a little bit smaller as you get to smaller and smaller scales. But the real concern is as those scales then push into the low magnetic Reynolds number case, they're going to be just sucking energy out of the field. And they're going to be a pit that we'll have to get around. And again, my argument was that hopefully the magnetic field exerts some influence on those flows, that they're not small scale anymore, that the magnetic field is essentially changing the dynamics and makes them big scales. That's the hope.
If you go back to the thermal histories that you showed,
yeah,
this is way too big a can of worms to open at 1237. But we have some constraints from geological and petrological history on the temperatures of the crust and the upper mantle.
That's right. Yeah.
And
so what would you be uncomfortable with these values? Maybe. Say 2 billion years ago, temperatures. Really, how much flux? So I've used here a value of maybe 3,800. But yeah, no, you're right. As I go back, there are certainly problems with this one. You think that's ruled out by the petrological observations?
Well, it depends whether the mantle does anything in between.
Right. So this is just the core mantle boundary temperature, right? At 3 billion years ago, the core mantle boundary temperature would have been maybe 4,700, right? 4,800. Pretty hot, right? Probably pretty molten. And to me, the other problem with this, with having an extensively molten area on the bottom, is that if these experiments are correct that suggest that the core is underdissolved in silicon and underdissolved in oxygen, it means that molten liquid is going to be equilibrating with the core like crazy. And there are consequences of that I don't think we see. And so, yeah, I think there are. I mean, you're absolutely right. There are constraints. But this is what you need to do. If this is how it works, and the inner core really starts here, then these are the sort of heat flows that we think we need with these higher thermal conductivities. We need those big values, unless there's another energy source, like compositional buoyancy, dissolving light element. And then a lot of these problems can go away. Basically, you're driving the thermal cooling of the core is only driving the exsolution of light elements, and that chemical buoyancy is what's mixing the core. And you don't need these high values of heat flow to get that amount of power. It could be. We may be missing the most important energy source in our problem. It's possible. So the mineral physicists and the geochemists need to do these experiments at 4,000 degrees and 136 GPa, and they need to do petrology at those conditions. And that would be great, actually. I commend that. Right now they're doing it in diamond cells, and it's really hard to control these things. You don't know whether you should believe these. I don't know whether I should believe these results or not. Yep, Ben.
So I think that Jupiter has a dynamo too.
Yes,
right?
It does. Okay, that's a good question, actually.
What are the Ekman numbers like there? Are those hard?
Tiny, right? But from an energy point of view, it's no problem because you've got metallic hydrogen, but then the layer above you is just like a fluid envelope, right? So it's no trouble getting the heat out. And so that's why all the gas giants have magnetic fields, or the ice giants too. It's because the bottleneck to getting the heat out is the mantle, the silicate rocky layer. In those guys, we don't have that problem. And so in those guys, they have big, large-scale magnetic fields. And Jupiter, presumably because of the stratification, the dipole is just right aligned with the rotation axis, right? So there's probably some additional dynamics that are separating us from the core in terms of making those observations. But the point is, what the terrestrial planets, where they struggle, is this bottleneck this crystalline layer has on getting the heat out when the core can conduct heat so effectively. And so you go to a giant planet, you've got gas, no trouble vigorously convecting and getting that heat out, and therefore all of those planets have magnetic fields. And so in some ways, it's sort of a consistent story. In some ways, to me, it's what's really surprising is Mercury, right? How does Mercury do this, right? If I was betting on that, I would have lost a lot of money on Mercury because I would have said no chance. You go to the small bodies like Ganymede, for example. How does that work? Small planet, small difference in temperature between the top and bottom. Thermal convection is completely inefficient. So is it compositional convection? Are you taking the container and kind of shaking it, spinning it, driving the flows with the boundaries rather than with buoyancy? Possible. Yeah. Or Dave Gubbins is right. Yeah. That's right. Thanks.